Great. Thank you very much. Welcome, everyone. And it's a pleasure to be able to speak to you today. I'm going to talk to you today about some trends towards the electrification of everything and how a new switch technology that we've created at Menlo Micro, smaller than a human hair, is going to change the way we do just about everything in the next century. But before we get into the challenges of the electrification of everything, I want to simply define something that we probably don't think too much about these days. And what is a switch? Why are switches important? And at the most basic level, when you think about switches, you probably think about the simple mechanical light switch in your house. These are the ones that you can see, but the switches that you maybe don't see so often do a lot more than that. Switches control so many things. They control all of our data, all the digital ones and zeros that are zipping around in data centers or in the highly complex processors that are in your smartphone or in your computers. They also control all the telecommunications signals, selecting and sending high frequency radio waves that stream our videos over the air. And most importantly, they also control power, routing all of our electricity wherever it needs to go. And you can find switches pretty much everywhere. In your homes, they manage and control your heating, the lighting, appliances are loaded with them, circuit breakers that protect everything. At your workplace, they control the elevators, the HVAC, servers, all the factories and all the machinery and the equipment that's inside of them. And in our transportation, cars are loaded with switches and relays, controlling all the motors for windows and wipers, managing the flow of electricity from the massive batteries, not to mention thousands of relays that are used in things like airplanes to pull electricity off the jet engine and route it to every seat back. All this is managed by switches, both large and small. And when you get right down to it, the switch is probably one of the most fundamental building blocks that is found in pretty much every electronic system. Now, the most common type of a switch or relay is electromechanical. And interestingly, the first electromechanical relays were invented almost 200 years ago, a full 60 years before we even figured out how to harness electricity. And what were they used for then? They were used for modern telecommunication systems of the day. Yeah, this is a telegraph. The operation of a relay is simple enough. You pass current through a magnetic coil. It creates a magnetic field that physically moves a large piece of metal or an armature from one point to another, and that helps to close the circuit. And there's literally thousands of different variants of this concept in use today, but they all pretty much follow the same basic principle. And amazingly, relays and switches were even used to build our first computers. There was a time when all the most complicated compute engines were built with mechanical relays or with a new type of a switch invented in the early 20th century called a vacuum tube. And these amazing machines took up entire rooms, but they helped us to win wars, doing things like breaking codes and aiming torpedoes. And this early version that you see on the screen here from the 1940s called ENIAC, this was one of the more famous examples. You can see its specifications here and the number of switches that it employed. But about 70 years ago, the world really got put on a different path that changes forever when the transistor was invented. The transistor was just yet again a different type of a switch. And these integrated circuits or semiconductors really changed the way that we manage data forever. It started us on a path of this digital revolution that we're still living through today. Just an example to compare to some of the original compute engines, and I'm sure most of you have heard of Moore's Law, but the number of switches that has been doubling every year for the last 50 plus years brings us to the point where we have billions of these things in a device that has just an enormous amount of compute power in minuscule amounts of power consumption and size weight. So that digital revolution that started with the transistor 70 years ago with a new type of a switch, what happened to power? And what's interesting to note is that the original electric grid was set up in the early 1900s. It really hasn't changed significantly since then, almost over 100 years later. It was mainly fossil fuel generation, one-way delivery of electricity to homes and businesses. The loads were relatively small, and there were very few plants that were spaced out geographically across the country. And when we talk about the next century, the way that we did things in the past is really not the way that we're going to need to be doing them in the future. We're going to have much more diverse sources of generation, like renewables that are coming online. There'll need to be much smarter communications between the generation and the loads, and communication in both directions. And we're going to need to develop much more complex, smarter management of local storage of things like batteries, which can not only charge up in your car, but can also provide power back to the grid. And this new network will need to be much more distributed, which will also help to make it a lot more robust. And just an example from recent history here, do we need any more evidence that having a more modernized and reliable electric grid is important? This example from this past week in the United States, in Texas, this is going to end up being one of the most expensive events in the history of Texas, probably costing over 20 billion in damages. And it's never been clear that having a reliable and intelligent grid with more advanced controls and redundancy will help to reduce the impact of these types of events in the future. And it's not only about redundancy and reliability. The number of electric loads that we're going to have to service in the future is going to grow significantly. And this term, the electrification of everything, is really referring to just that. It's taking applications that today might rely on fossil fuels and moving them back to electric, whether it's your vehicle or your home heating, cooking, water heater, etc. This is going to put an enormous amount of stress onto the system. And in this graph that you can see here, it's going to push forecasted to push our electricity consumption just in the US by close to 50% by mid-century. And that's just 1/6 of the worldwide total. So it's going to be even more important than ever before to develop some intelligent controls and really put a much tighter focus on energy efficiency. So what kind of switches do we have for controlling power? Well, unlike the digital revolution that we talked about, the switches and relays for controlling power have not had anywhere near the amount of innovation as we've seen for data. This diagram that you see on the left is from one of Thomas Edison's original patents for a relay in 1873. And on the right-hand side, you can see a typical example from modern day technology. Now, this is almost 100 years after Edison died. And it's essentially the exact same architecture. It has a coil, it has an armature, moving metal. It's the same idea. And honestly, if Edison was to come back to life, I'm sure he would be, not sure if he'd be proud or horrified that he could very easily recognize essentially the same technology that he was using in the 1890s for routing electricity from point to point. So it really seems like Moore's law has kind of passed us by on this particular application. So I want to tell you a little bit about what we're doing at Menlo Micro. We're taking inspiration from the Wizard of Menlo Park himself, Thomas Edison. It just so happens that between 1870 and 1890, Edison created over 200 patents for things like circuit breakers and relays and switches. And as we know, Edison played a huge role in the electrification of the entire world that happened in the first half of the 20th century. And it's that heritage and over 100 years of subsequent innovation at General Electric that brought us to the point at Menlo Micro of reinventing the switch yet again. So who is Menlo Micro? We're a fabless semiconductor company based in Irvine, California, but our technology for what we call the ideal switch was created in the R&D labs of GE. And the ideal switch is the world's smallest, most reliable, and most efficient micromechanical switch that can be used for power. You can see it in this graphic here. It's smaller than a human hair, but can handle thousands of volts and tens of amps of current. And most importantly, what you can see is that we can build dozens or even hundreds of these onto a small chip and then wrap them up into a small package that can be easily integrated into advanced power switching and controls products. And the performance of these switches allows us to bring some very disruptive, not performance, but also efficiency gains for applications like communication systems, but also for power electronics as well. So to just define for you what we mean by ideal switch, the perfect switch has always been something of the holy grail for the electronics industry for a very long time. Some basic characteristics, a perfect switch would be, when it's on, it's just a piece of metal. There's no resistance at all. When it's off, you have a open circuit, it's broken, and you have an air gap. And ideally, it would take no power to turn it on and to keep it on. And we're not quite there with our ideal switch, but we've made some significant strides in being able to make these extremely low loss. They're very high isolation when they're open, just like a mechanical relay. And most importantly, they have electrostatic actuation, no complicated coils. And so they're very low current to operate them, which makes them extremely efficient. They're small, fast, silent, and another key differentiator is the lifetime. These switches can turn on and off billions of times, which is thousands of times longer lifetime than a traditional mechanical relay. And one of the things that we did borrow from the semiconductor industry is that we manufacture these micromechanical relays in a semiconductor-like process, which means it's very scalable, can scale up to very high volumes, and can drive down the cost significantly. And just to highlight some of the main differences between traditional switches that have been used for switching power and the ideal switch, apart from the obvious size differences, which make traditional power switches very difficult to integrate into miniaturized electronics, the mechanical relays are slow, they have limited lifetime before they need to be replaced, and they require a lot of energy to move that massive piece of metal, the armature, which controls the flow. In recent years, there's been solid state versions of these that you see in the center here that solve some of those problems. But the fact that you're pushing an enormous amount of current through these devices, and they're really a semiconductor device, it translates to very large power losses, which generates a lot of heat. And that's going to be a challenge for some of these next generation efficiency objectives that we have. So the ideal switch is really combining the best attributes of both of these technologies into a miniaturized package. And we have examples where we can reduce the size, weight, and power losses by over 99%. So just to give you a simple example, take the smart outlet. These somewhat bulky add-on devices have been proliferating quite a bit over the last few years. But when you get right down to it, how can we build smart, integrated, advanced control systems for the next century around a switch technology that has been around and really unchanged for the last 150 years? If you look inside one of these smart switches, you might have some of these in your home, you'll see that almost 1/3 of the product area and more than half of the height or the width, the thickness of the device is taken up by an old-fashioned mechanical relay. And this simple calculation that I'm showing here is just showing from an efficiency perspective the relative impact if you were to upgrade these smart electronics into all the outlets and just in the United States that were converted to this type of a relay device versus using an ideal switch. The efficiencies really add up. And when you think about it in terms of volumes, there's billions and billions of outlets, but there's also billions and billions of other relays that are used in applications like automotive and industrial sectors. So really improving the fundamental efficiency of such a fundamental building block of all these electronic systems is going to really help us to achieve our electrification goals in the future. So someone had asked me, what's the world going to be like 50, 70 years from now? It's really hard to say, but when some of the luminaries like William Shockley and Jack Kilby and Robert Noyce, who invented the transistor and the integrated circuit back in the 40s and the 50s, effectively creating the modern semiconductor industry, they probably had no idea that simply inventing a new kind of a switch was going to lead to this digital revolution that we've been living in for the last number of years. And as we look forward, the problems and the challenges over the next century in the power and in the telecommunications infrastructure side are going to be enormous. And system designers are going to need new tools to be able to solve them. And while here at Menlo Micro, we have a pretty clear vision of what we'd like to do with the ideal switch over the next 5 to 10 years, we're really just excited to get this technology out into the world and see what some of the world's most talented designers will be able to do with it. And with that, I'd like to say thank you very much for listening.